Hello everyone. So wonderful good evening to all, and I'm really happy and excited to discuss about this paper. And this paper is proposed in 19 May 2016. And okay, so in this paper, we're gonna learn about what is attention mechanism and from where it proposed and who proposed and what is this complete mechanism of attention. And nowadays it is booming day by day and in many applications many areas, so we're gonna learn about this attention mechanism from this paper. Okay, so first of all, what is attention? So attention is action of selectively concentrating on a few relevant things, right? So what is attention? Action of selectively concentrating on a few relevant things while ignoring others. So let's say here learning is our main focus, so this is focusing on one terms while ignoring others, right? So in this way, before at no but what was problem with and why they introduced this attention? So there is something like before attention model, that because this model was proposed in 2015. So before this model, machine learning translation was on encoder decoder, RNN and LSTM base, right? So here also they are saying that before that paper proposed, the mainly task was doing using this encoder decoder model. Okay, so neural machine translation was based on encoder decoder, RNN and LSTM. So but how encoder decoder, LSTM and this is encoder decoder base, RNN and LSTM. So before attention, it was into existence and lot of work were finished by using these things, encoder decoder mechanism, RNN or LSTM. So it was working following two ways. First, uh, this encoder part. So let's say this is your encoder part, and one is your decoder part. So because this is encoder decoder base, so let's say this is encoder part and this is your decoder part. So the encoder LSTM is used to process the entire input, complete input sequence. Let's say you have any sequence, input sequence, so it work on complete input sequence, right? So it takes this input sequence and then it encode, because this is encoder, so it encode it into a context vector. So here in the last layer of this encoder, it have a context uh, vector layer. So I mean that layer treated as context vector. Okay, so which is the last hidden state of LSTM or any RNN. So we are uh, what we need out of this context vector, that our representation or this sentence we have inputted in this encoder, and after that it is saved in context vector, it should have a good um, summary. So here we need good summary, and this good summary is inputted as in uh, decoder. So this is our decoder model. So this good summary is inputted into decoder, uh, and this decoder will produce the translation. So this is our converted translation of one language, one sentence to another language sentence. Okay, so so right, so this is like encoder decoder based process, how it is working. And the decoder part or LSTM part, a unit produce a word in the sentence one after another. It's like one word after another word. Okay, so this will produce a translated output. But this encoder decoder model that we have, uh, there is some drawback of this. So first drawback of this is evident. Means if encoder will give this, it will not work good. Means we are expecting that its output of context vectors would be good summary. But what if it will not learn that? So the main drawback of this approach is evident because if encoder make a bad summary, then translation will also be bad. So it depends on how this encoder are making summary. So if it is good, then translation is good. If it is bad, then translation is also bad. All right. So this is one drawback. So what when this drawback comes into existence, when you have a longer series. So let's say you have a long sentence, so then it fails to learn a good summarization and it will produce a bad result. So that's why we can say this RNN cannot remember longer sequence due to Van Hertzing gradient or exploding gradient problem, because it can remember the part which is just seen, not a previous part or a very earlier part. It will just remember whatever it have just seen. Okay. So after that, there was one author in 2014. So he who proposed the encoder decoder network, demonstrate that, I mean they also demonstrate that this will this encoder decoder network degrades rapidly as the length of input sentences increases. So this is what this Chow et al. Author said, uh, that long it is not good for longer sentences, right? So that's why after that, another problem after that, there is one more things like, because it was good for first drawback was longer sentences, vanishing gradient problem, and it was not. Another problem is that there is no way of give more importance to some of the input words. We have to input complete sentence here and will produce a complete answer. So there is no concept of attention, that is more importance. So because we know in every sentences we have some words that is more important than the other, so there is no concept in encoder decoder based model. There was no concept of giving importance to any particular words, some of the word compared to other while translating the sentences. So then this paper proposed by uh, this author from Jacob University, Bremen, Germany. So this author proposed a simple but a elegant idea where they suggested that not only can all the input word be taken into account. We don't need complete words. We don't need all words into account in context vector, but relatively importance should be also given to each of them. So not only see, not only we can give complete sentences to this, we can also give its corresponding importance. So whenever the proposed model generates a sentence, it searches for a set of position, as usually, and in the encoder and the hidden states where the most relevant information is available. So here we can include the concept of attention. So go look at this paper further. So here what it suggests. So this is about like it introduces the concept of uh, introduces the concept of attention, and here they are saying that what was the problem of earlier, what was problem and why they introduced this. So these was some of the problems that I have discussed, drawback of encoder decoder based model. So that's why this paper introduces uh, their concept of attention. So in this paper, here you can see in this paper they show that the proposed approach is jointly learning that align and the translate achieves a significant improved translation performed over the basic encoder decoder approach. Okay, so the improvement is more apparent with longer sentences, but can be observed with sentences of any length. So this is this task showing the English to France translation here, and the proposed approach achieves with the single model and translated performance comparatively comparable and close. So these were experiment that I was talking about, that this paper said that before attention, or before including the concept of this, for the longer sentences performance was poor. Okay, so this is some of the previous models and the background of this things, that what was problem with encoder and decoder, and it was fails to learn the prior words. It just learn, it can only remember whether you talk about LSTM or whether you talk about RNN. So in both cases, the problem is they just forget complete sentences from the prior and just remember what is recently seen. Okay, so that was problem. So this is encoder decoder base, encoder decoder, RNN encoder decoder. And in this this Chow et al, that I have said recently, that they proposed that encoder decoder model, and he demonstrated that, Chow et al demonstrate that the performance of the encoder decoder network degrades rapidly as the length of the input sentences increases. Okay, so here x is equals to sequence of vectors it have, in once it included inputs, it input a sentence, and a sequence of vector will be in x equals to x to 1 and vector into a vector c. And the most common approach of RNN is xt, and it's ht minus 1. So this will be in this in ht. So where ht is a hidden state at time t, every time t it is a hidden state, and c is a vector generated from the sequence of the hidden state. And f and g are some non-linear functions. So here f and these are functions, nonlinear functions. So it used LSTM as f. Here they have used LSTM, and then yeah, as and q h t hidden q means function of hidden states is equals to capital ST, for instance. All right, so so this was about background we were discussing. Yes, right. So now the decoder is often trained to predict the next word yt and the context vector c, and all the previously predicted word is in y1 to t minus 1. So it is like the decoder defines the probability over the translation y by decomposing the joint probability into a ordered conditionals. So here the concept of prior probability, and where y equals to y1 to t, where the RNN each conditional probability is modeled as. So this is a model conditional probability model, and here this function is also a non-linear and multi-layered function that output a probability of yt, and st is a hidden state. St is a hidden state of the RNN. It should be noted that other architectures such as hybrid of an RNN and a deconvolutional ladder can be used, right? So let's understand the learning to align and translate. So in this paragraph they are giving concept of attention. Okay, so this is a diagram of attention, and here is by LSTM, bidirectional LSTM used here to generate a sequence of annotations. So these are sequence of annotations from h1 h2 h t. Okay, So LSTM they are using for each input sentences. So every input sentences LSTM is used here to generate a sequence of annotations. So it will annotate that, it will provide, and all the vectors h1 h2 up to ht is here used in their work as basically the concatenation of forward and backward hidden states in the encoder. So this is bidirectional, so it once it will forward and then backward and then forward, in this way it will work. And here h in some intermediate state, let's say hj. So hj is used for some hidden backward forward operation, like some of the operation is performing. So to put it in simple, all the vector of h1 to htx are representation of tx number of word in the input sentences. So in the simple encoder decoder model, only the last state of the encoder LSTM was last state of LSTM was used as the context vector. And what is this last state is htx. So this is last state. So this last state is used as LSTM as context vector. Okay, so but the thing is, this paper emphasizes on embedding all the embeddings of all the word in the input. So all the word in the input means represented by hidden state. So this emphasis on embedding of all the word in the input and while creating the context vector. So once we are creating this context vector, it will embed all the word in the input, or whatever word from the sentences we have, and did this by simply taking the weighted sum of hidden state. And then what it is taking it, they did this by simply taking a weighted sum of hidden state. So and the weight is also learned by feed forward neural network, and also the context vector ci will be, so this is like context vector ci for the output y word wi. Okay, so context vector ci for the output word wi, we have wi as output vector, is generated using the weighted sum of the annotations. So this is weighted sum of annotation aij hj. So aij is annotation, and hj is corresponding word, corresponding vector. Okay, so weights aij are computed as so let's say the weight is aij of each annotation hj. So hj is annotation and aij is weight. So the weight aij computed by softmax function. And what is softmax function equations? So this equation they are following as a softmax function. So aij weighted weights can be this exponential of eij over the summation of k equals to 1 to tx exponential of eik. Okay, and what is this eij is the output score of a feed forward neural network. So this is output of score of feed forward neural network described by the function a. And this attempt to capture the alignment between input at j and the output uh, at I. So this is the part alignment model is an alignment model which scores how well the input annotations position j and output at position I match. Okay, so this is a score is based on rn and hidden states. Okay, and jth annotation hj of the input sentences. Good. And then Then if the encoder produces a tx number of annotations, let's say it is producing tx number of annotations. uh, Annotations means the hidden state vector, so each having dimension d. If it have dimension d, then the input dimension of the feed forward neural network will be tx 2d. Okay, so this is like decoder is also having d dimension, and these two vectors are concatenated. So this input is multiplied with the matrix wa of this 2d one dimension concept. So here you can see these things. Okay, so let's go through this paragraph once, because this is very important section. So until that we have seen that this is a preconditional probability, and this is RNN hidden state. SI is an RNN hidden state for time I, particular time I, what is hidden state, and CI is context vector, and YI is targeted output of encoder decoder models, and it is depend on the annotations of H1 to HTX. Okay, so that we have, and then we also have seen that the context vector Ci then computed weighted sum. So context vector Ci is computed as weighted sum of this annotation Hi. So this is annotation formula, and then we have seen that this annotation includes this yeah, so this annotation includes what the called softmax function, sorry. So this annotations Aij are computed by softmax function by giving this equation. Okay, so here also you can say Eij is computed as A of S I minus uh, Si minus 1 Hj, means Eij is the output score of a feed forward neural network. This is output score of feed forward neural network described by this function A. So this function is A, and it is described by an attempt to capture the alignment between J and the I. So this is I, this is J. So it is trying to align the capture the alignment between these two, I and J. So that's why we can say this is alignment model, and which scores how well the inputs are around position J. So we have seen these things, and yes, and then what else? Hmm. Also we can say that like Eij score that we are calculating score is a tan hyperbolic function is applied by a softmax function. So tan hyperbolic function can also apply for this output. So I think indication have been given for that tan hyperbolic function. Okay, right. So here is a concept of this attention in this. So I think it is a good to go through this paragraph, and so before that we have seen that alignment is not considered as a latent variable. So instead the alignment model directly computes a soft alignment, which allows a gradient of cost function to be back propagated through, and the gradient can be used to train the alignment model as well as the whole translation model jointly. So we can understand the approach of taking a weighted sum of all the annotations as computing an expected annotations. Okay, so where the expectation is over possible alignment, let I is a probability that the target word y is aligned to or translated from a source word xj. So here a concept of weight is come into consideration. So then the ith context vector Cij is expect annotation over the annotation with probabilities. So this will be the concept of attention here with weighted annotation or annotation. So the probability Aij or its associated energy Eij reflects the importance of annotation Hj with respect to the previous hidden layer, hidden state in deciding the next state Si and generating Ya in Ya. So this implements the mechanism of attention in the decoder. See, this is important things. So this in this way, while applying this weight vector and this annotations with probability, so this will uh, give the concept of attention in decoder. So decoder decides part of the source sentences by pay attention to, and by letting the decoder have an attention mechanism, relieves the encoder from the burden of having to encode the all information in the source sentences to fixed length vectors. So with this new approach, the information can be spread throughout the sequence of annotations, which can be selectively retrieved by decoder accordingly. All right. So and this is a concept of encoder with this bidirectional RNN for annotating sequences. So I think we should also go through this portion. So what is happening in this portion, and so let's start with okay. So yeah, yep, right. So the encoder produces TX. Number of annotations. From previous paragraph we have seen that encoder produces tx number of annotations. Annotations means hidden state vectors of each having dimension of d, and then input dimension of the feed forward network is tx 2d. So that will be the input dimension. Okay, so 2D because it is feed forward neural network to right. So in which, assuming that the previous state of the decoder also has D dimension, and these two vectors are concatenated. So this input is multiplied with matrix WA, and once it will multiply with a vector WA. Okay, so of WA of 2D one dimension, so to get the score of EIJ. So this score of EIJ we have seen. So it have dimension of tx comma 1. So on the top of this EIJ score, a 10 hyperbolic function is applied, that we have seen 10 hyperbolic function is applied to this, and so then it will give expectation of, yes, so then it will give once EIJ score we have, then after that we have hyperbolic function applied to a softmax, we have normalized alignment score, and this normal alignment score will be uh, their weighted sum. Okay, so that was something about. So let's go through once we, I think we should go through this. So the usual RNN described in equation 1. So what is equation 1 is this. So this is usually RNN. Okay, and then it is saying that it reads an input sequence x in order starting from the first symbol xi to the last one xt. And however, in the proposed scheme, we would like to annotate of each word to summarize not only the preceding word but also the following word. So that's why for it is using bidirectional RNN, because for preceding word and for the following word. And with so that's why they have included the concept of bidirectional RNN, which has been successfully used recently in speech recognition. So RNN consists of consists of forward and backward RNN, and the forward RNN is described as vector of f, reads the input sequence as order of x1 to xt that we have seen in previously, and calculate the sequence of forward hidden state. And the drawback of RNN drawback are, and the backward RNN after reads the input in the reverse orders. It will read the input in the reverse order, so resulting in a sequence of backward hidden state. So it will have a forward hidden state and it will have a backward hidden state. So two hidden states we have in this diagram. You can also see this. One is for forward hidden state, one is for backward hidden state. Okay. They obtain an annotation for each word xj concatenated in the forward hidden state xj, and the backward one is hj backward, forward is for hj forward. That is hj is equals to so complete hj is equals to both forward and backward hidden state. In this way, the annotation as contains a summary of both preceding word and the backward following word. So, due to the tendency of RNN to better represent in recent input, the annotation SJ will be focused on the word around XJ. So, SJ will focus on word around XJ, whether it will be in forward and in backward. This sequence of annotation used by decoder to align model later to compute the context vector. So this was a complete diagram description of this diagram, how and what is happening in this. And then they have done some experiment. Let's say these experiment. So for the experiment setup, they have evaluated the proposed approach on the task of English to France translation. And to do the same English to France translation, they use a bilingual parallel corpora provided by ACL VMT 14. This is data set VMT 14, and they have reported the performance of RNN decoder and code decoder, which was proposed by recently. And also they use the same training procedure and same data set for both model without attention and model with attention. So like something about data set contain the following: English to French parallel corpora and Europal 61 million word news commentary UN, and two crowd corpora of 90 million and 272.5 million word respectively. So totaling 180 totaling 850 million words following the procedure described in this paper. So they reduce the size of the combined corpus to this 348 million words using the data section method. And they do not use any monolingual data other than mentioned parallel corpora. So although it may be possible to use a much larger monolingual corpora to pre-train an encoder. So okay, so the BLE, this figure shows the BLE score of the generated translation of the test set and the respective to the length of the sentences. So the result are on full sets, which include sentences having a known word of models. So this some models and they have used and find calculated the VLE score. So for the task of this, they have okay, let's read this thing also. News 2013 to make the development validation set and evaluate the model on the test set from VMT 14. So which consists 3 sentences not present in the training data set. So after a usual tokenizations, they use a sort list of 30,000 most frequently word in each language to train on their models. So any word not included in the sort list is mapped to a spatial token. So they do not apply any other spatial processings such as lowercasing or stemming to the data. Okay, so model they have used is two models. Okay, so two models means first one is RNN encoder decoder model. Okay, and other model is their proposed model, which is refer as RNN search. They are calling it RNN search model. So they train each model twice. Okay, two times they have trained first with the sentence of length up to 30 word, and then with the sentence of length of up to 50 word. So two times they have trained each model with 30 word or with the 50 word sentence. Okay, and the 30 and 50 word sentences of they have used RNN and code 50, RNN search 50. Okay, both for both model. For 30 word they are saying that RNN code 30 and RNN search 30. Okay, so the encoder and decoder of RNN encode have 1,000 hidden units, and the encoder of the RNN search consists of forward and backward recurrent neural network, each having 1,000 hidden layer, and its decoder has 1,000 hidden layer. Okay, both have hidden layer, 1,000 hidden layers. In both cases, they use a multi-layer network with a single max out hidden layer to compute the conditional probability of each target. So for calculating this attention conditional probability of each target word, we use this concept. So they use a mini batch stochastic gradient descent algorithm together with added delta to train each model. Okay, so remember this stochastic gradient descent together with added delta for training. So each SGD's update direction is computed using a mini batch of 80 sentences, and they train each model for approximately 5 days. So it's a long time. 5 days, not a quick demonstration. It's really a hard and day taking time training. So once a model is trained, they use a beam search to find the translation that approximately maximizes the conditional probability, and these two people use this approach to generate translation from the neural network model translation, and after that they have the qualitative result, and they have calculated this BLEO score for calculating the performance, and these are BLEO scores. So four sample aligned found by RNN search 50. The x-axis, y-axis of each plot correspond to word in the source sentences. So these are word in source sentences. Uh, okay, so this is X label. So this is word and source sentences. Okay, and these are generated sentence word and this generated sentence. Each pixel shows the weight. Every pixel is showing weight ij of the annotation of jth source word for the ith target word. So this is annotation, weight annotation, that it have a large weight, it have less weight, it have whatever it is. So uh, in grayscale, 0 black, 1 white. So this is probability from black to white, means if it is 0 have less probability thing, and up to 1 means as brighten, and as white means larger weight it have. Okay, so arbitrary sentence B to D, three randomly selected samples taken from among the sentence without any unknown word. So they have done a experiment on 10 to 20 word from test set. So one of the motivation behind this proposed approach was use of fixed length context vector. So in this basic encoder decoder approach, so they conjecture that this limitation may make the basic encoder decoder approach to underperform with long sentences. So and they see that the performance of RNN encode decode dramatically drops as the length of the sentences increases. Once the length of the sentences increases, it will drop. Performance of RNN encode decoder will drop frequently. On the other hand, both RNN search and RNN search 50 are more robust to length of the sentences. So these two are their proposed model. And RNN search 50 especially shows no performance deteriorations even with sentences of length 50 or more. The superiority of the proposed model over the basic encoder decoder is further confirmed by the fact of this. So it is showing that this search model perform better than the encoder decoder. So if compared to encoder and RNN encode 30 performance also poor, and for RNN search it is better than simple encoder decoder, and same for RNN search 50 performance is better than this. For all, for this also performance is improved, and also for Moses performance also improved. Okay, so these are some qualitative results, and we have shown that performance decreases as the length of the sentences increases, and this was complete concept of this attention mechanism proposed in this paper. And the conclusion is that they have proposed a novel architecture that addresses some of the issues like length of uh, encoder decoder model was not able to perform well on long length. So that to reduce or to overcome these kind of issues, they proposed the models. So they was same, and they tested the models on RNN called RNN search on English to France translations. Okay, so this is something about that they have done lot of tasks. So it's a nice paper, good paper, and I hope you'll go through this paper once. It's a literally very knowledgeable paper. You'll get lot of thing once you go through this paper. And for today this is all, and in next paper we'll learn some further concept which were using this phenomena of attention network. Till that, thank you everyone. And please like, share and subscribe my channel also. Bye bye.